So let us now talk about one-way ANOVA. So what is one-way ANOVA? ANOVA is basically analysis of variance. That is what ANOVA stands for. And we are doing one-way ANOVA. That means we are only one independent variable. Like we could have one independent variables and we are looking at that independent variables for other different groups that we are analyzing. So we also have what is called two-way ANOVA, which is looking at two independent variables. And then we also have something that is called MANOVA when you are looking at different dependent variables. So here in this case, we only have one independent variable, and that is what we are going to look at. Previously, we have talked about independent and dependent sample t-test, and in that case, we only had two groups. So think about doing nearly the same, comparing the means, but in this case, we have more than two groups and a single dependent variable. So one-way analysis of variance when comparing more than two groups on a single outcome variable. Your outcome variable is your dependent variable. So it is one way because we are only examining on one factor. That means one independent variable or the grouping variable. Let me take an example and explain it to you. For example, we are looking at math achievement, okay? And our grouping variable, it then becomes, we are looking at 4th grade, 5th grade, 4th grade, 5th grade, 6th grade, 7th grade. So you have 4 groups, but I'm only one independent variable, which is my grade level, okay? So if I have my grade level, I can say my groups are 0, 1, 2, 3, 4, but I only have one independent variable. Let me give you an example of when there are more than one independent variable, just so that you guys have an understanding of it. So an example of it would be if I am trying to find out a weight of a group of 20-year-olds. Okay, I'm trying to find out the weight of group of 20-year-olds. So in this case, my independent variable would be gender. So whether they are male and female, but it will also be the month. So I'm looking at January, February. So in January, I'm looking at male and female. In February, I'm looking at male and female. In March, I'm looking at male and female. So what is happening is I have two independent variables here. I have the month and I have the gender. And then both of them, how do these both relate to the dependent variable of weight? This is going to be an example of two-way ANOVA. So you are not going to be doing a two-way ANOVA. You're not going to be doing a MANOVA, in which, let's say, a MANOVA will be two dependent variables. So I suppose have gender, but I am looking at their achievement, academic achievement, and I'm also looking at, let's say, self-efficacy. So I have two dependent variables there. So there are different things that you can do when you have the different types of ANOVAs. But here we are going to concentrate only on one-way ANOVA. In this case, I have one independent variable or one grouping variable. Independent would be my groups that is going to make, and I have looking at their dependent variable. But the groups are more than two. That is why I have to end up doing an ANOVA. So like here, if you can look at that symbol here, that means I have three groups here. I have a treatment 1 that I do and a group 0. Treatment 2 that I do, I have a group 0, and then I have a control group. So I have two versions of a treatment group to a control group. Another way that you can look at this is if I want to check, like if I have 3 or more categories of independent variables and I want to check how does that single intervention affects the different categories. Like if I have age as a category and I have 20-year-olds, 30-year-olds, 40-year-olds, 50-year-olds, and I want to see how 15 minutes of exercise affect them. Okay, So I do 15 minutes for each group and I see. I'm a math person, so here I have a math example. There are 4 different math classes, and then you want to check whether these 4 different math classes, what is their effect on a math test. So you do the same math intervention, like maybe I do it for 15 minutes for one, 20 minutes for another one, 30 minutes for another one, and I want to see if there is a difference. ANOVA is also useful in correlational research if I want to see that the difference is intact within the group. That means that I have done a grouping variable. I have a nominal grouping variable. Nominal, it is not dichotomous because I have more than 2 groups. It is a nominal grouping variable and a continuous dependent variable. And I want to see whether the experience or the correlation between the groups is intact. And so then I will do an ANOVA. So one thing that is really very important to keep in mind is that if your ANOVA is statistically significant, if the p-value comes out to be less than 0.05, which we will set as our level of significance, that means that there is a difference in means somewhere, which is called omnibus difference. There is a difference. You don't know whether group 1 is different than 2 or 2 is different than 3 or 1 is different than 3. You just know that there is some difference somewhere. There is statistically different in some way. So one of the most common thing that follows an ANOVA is either you do a planned contrast or post hoc contrast, post hoc test. Planned contrast or post hoc test. When we do post hoc test, there is no strong hypothesis. We don't say that this group is, their mean would be more than the other 2 groups, or this group would be less than the other 2 groups. We do not have a strong hypothesis. But in a planned contrast, we do have a strong hypothesis. So you follow an ANOVA with either a planned contrast or a post hoc test. You never do both of them. You only do one thing. So you decide which one you want to do, but you never do both those things. So the data file for this ANOVA is already uploaded, and the example for this data is actually taken from the book that is called Discovering Statistics by Andy Fields. It's a very famous book. And so what it is in this data set, is there are 3 groups. There are 3 groups of men. One group receives a placebo, one group receives a low dose of Viagra, and the third group receives a high dose of Viagra. And the dependent variable is the measure of their libido. So if we look at the group, each group has 5 participants. Okay. Each of these participants are different because it cannot be that the same person can be in the placebo group also, low dose also, or high dose. Okay. So all these are different. And this is placebo group that does not receive any dose, is called, their libido measure is this. This is the low dose group that receives the low dose of Viagra. This is the high dose, that means they receive the high dose of Viagra. So this is a diagram that is actually taken from the Andy Fields, not a diagram, the data set that is taken from Andy Fields. I have a picture which has their mean and variance and variance score, and you will notice that this is the sample mean and the sample standard deviation and the sample variance. When we have population, we talk about mu SD, and we have the sigma square. So look at the symbol, tells you this is the sample one that they have talked about, and here is the grand mean. Okay, so I put this data set in my SPSS. Let me minimize my. So here it is in SPSS. So as you can see in this data set that we just looked at, this is the people, and there are 15 people. So remember how we had 5 for placebo, 5 for low dose, and 5 for high dose. So here we have actually all the 15 people. And if you look, you have one group of 5, like 1, 2s, and 3s. So if I show you my variable view, you will see that 1 means they got the placebo, 2 means they got the low dose, and 3 means they got the high dose. So here is my 5 people with placebo, 5 people with low dose, and 5 people with high dose of Viagra. So placebo, low dose of Viagra, high dose of Viagra. And here is their libido. And so if you look at this, I just took these values and put it in a straight line like this. So when you look at your D2L, you are going to actually see a SAV file with this data set and also an Excel sheet with the data set. Once again, I want to make sure you guys understand that you do not have to do any SPSS. I am doing all the SPSS. SPSS is costly, and so you don't have to buy the software or do SPSS. If you have it, this actually provides you with an opportunity with the data set already done so that you do not have to transfer or do anything about it. If you want to work on Excel, because lots of people use Excel also to do the actual formula and find it out, you are welcome to do that. So that is why you have that over there. So here is my data set. Before I even start anything, I have to look at what is the research question. So let's go back and see what is my omnibus question. Remember what omnibus difference was, is there is a statistical difference, but we don't know where it is. So here's the question. Is there a difference? This is a mistake. There should be no B here. Is there a difference in average, that means the mean libido, between participants who get the placebo, a low dose of Viagra, or a high dose of Viagra? So is there a difference in the participants that have placebo, low dose, and high dose? So this is just our research question, but then we can either do post hoc test or planned contrast. Here I have given you both those so that you guys can actually look at how these questions are. So post hoc comes with no strong hypothesis. So if there is an overall mean difference, that means if there is a statistical difference, which groups have statistically significant differences? So it is comparing the groups, and I don't know which groups have it. So this is a post hoc. But the planned contrast is, if there is an overall mean difference, will there be statistically significant linear increase among those who get the placebo, a low dose, and a high dose of Viagra? So here it is we use between when there are 2 groups, but we use among when there are 3 or more groups. Okay. So here we have, because remember how we were talking about, is there a difference between this and the other groups in independent and dependent variable? But when we have more than 2 groups, more than 3 groups, we use among. So that is why that verbiage is used. You don't have to put a superscript and give that. This is for you guys to understand as to why there it is. Okay. So this is where it is coming from. So once again, I have my research question, I have a post hoc, I have a planned contrast. Most often researchers do post hoc test because they don't plan for a difference, or do not most often. And that is what probably you guys will also be doing, is if you end up doing an ANOVA, you will be doing a post hoc test. But here is what a planned contrast looks like. So I had my research question. I have to have the null hypothesis. So same way, the null hypothesis is there will not be a difference. So basically no difference is my null hypothesis. Not be a difference in average libido between participants who get the placebo, a low dose of Viagra, and a high dose. So basically, it is saying mu1 is equals to mu2 is equals to mu3. The mean difference in, or the mean of the libido who get the placebo, mu1, who get the low dose, mu2, who get the high dose, mu3, is going to be equal. Okay. And so the post hoc hypothesis, because we were talking about which groups are significant. So this is the hypothesis, the null hypothesis for that. It'll be, so it can have any one of these three, right? Not statistically significant difference between placebo and low dose. So we are now saying mu1 equals to mu2. Here we are saying mu1 is equals to mu3. Here we are saying mu2 is equals to mu3. So basically, the post hoc, we are comparing, we have three groups and we know there was statistical difference. So now in the post hoc hypothesis, we really don't have a plan as to what could be a difference, right? So what we say is mu1 could be equals to mu2, or mu2 equals to mu3, or mu1 equals to mu3, because we set up a null hypothesis in a way to reject the null hypothesis. So in this case, we have no idea what we want to say. And here it is saying there will be not a statistical significant linear increase between placebo, low dose, and high dose. So in planned contrast, our hypothesis was that the libido will increase linearly. For placebo will have the least, then the low dose, and then the high dose. So it's going to increase linearly. That is what we want to see in the planned contrast. So our hypothesis would be that it would not be statistically significant increase. Null hypothesis is set up as being no difference. There will be no difference. There will be no statistical linear increase. There will be no difference between the means. That is how you set up your null hypothesis. So after that, even before we run the test, now we have to set up our criteria for accepting or rejecting, or we should say rejecting or failing to reject the null hypothesis. So we say I will reject the null hypothesis if the p-value associated with the F statistics is 0.05 or less. So equals to or less than. If homogeneity of variances is assumed, remember that was an assumption. If homogeneity is not assumed, then I will reject. So let me talk about the Brons-Forthway test and the Welch test. Okay, so let me open up the document that was the assumption document and what analysis to be done. So here is the assumption chart. Remember how we had 4 assumptions for independent and then we had assumptions for dependent. So same way, we have assumptions for ANOVA. We have assumption that sampling distribution of differences between the squares should be normal, which is again the normality. We have the KS test. We have the visual analysis through the histogram. So here's the same 3 conditions. Visual analysis through the histogram. N is greater than equals to 30, KS test. And then we assume normality if P is greater than equals to 0.05. So here we already know that our N is not greater than 30 or equal to 30 because we only have 15 participants, right? The data measured at least at the interval scale, which is yes, because we have the dependent variable libido in the interval scale. And then here is the homogeneity of variances and the scores are independent. And so if these assumptions are not met, we do what is called the Brons-Forthway test and the Welch test. Okay. And so we are not going to do those tests. We are not going to go to the statistics. We are only going to go through the statistics with and one-way ANOVA when the assumptions are met. Okay. So let's go down. So post hoc test. So we also have to think about what post hoc test to be done. This is taken from, once again, Andy Field's Discovering Statistics. The most common post hoc test is done is the Tukey. Tukey is the most common. The one done is when the sample size are similar, which is similar, 5, 5, and 5 within the 3 groups that we have. And homogeneity of variance is assumed. So this is the most one done. if the sample size are different, that means if one had 5, another had 10, another had maybe let's say 12, then the Gabriel's test for post-hoc is done. There is also another one. If they're slightly different, we have Gabriel's, but if they are very different, then we have like if I have 5, 20, one is like 30, we do, because 5 is very different from 30. So that is when we do the GT2 test. If there is no equal variances, then we do the Games-Howell procedure. So there is a lot of ones that you can do, assuming or whatever happens. We are going to focus on the Tukey post-hoc test. So for each of the statistics, we will reject if value is 0.05. So that is what happens. Now, in the terms of planned comparison, we will reject if p-value is contrast is 0.05. So planned comparison is just one of them. So as we were just talking a few minutes back about the assumptions. So what have we done till now? We know our data set. We've put the data set in SPSS. We have a research question. We have that if that research question, if we have the criteria of rejection, the level of significance, p is less than equal to 0.05, and if that turns out that we reject the null, because we have a research question and the null and the level of significance. If we reject the null, then we have a postdoc test question, research question, and a planned contrast research question. We also have what test we are running. For the research question, we are running the OneWay ANOVA test. For the postdoc test, if the equal variances is of the homogeneity of variances is satisfied, we are going to run the Tukey test. And if we are doing the planned contrast, we already know we are going to run this test. So what we now need to look at is the assumptions. So assumptions, if we are looking at the assumptions, these are the assumptions that are stated. In terms of normality, what matters is that distributions within groups are normally distributed. So I want to look if they are normally distributed within groups. The data measured is at least at the interval level. There is homogeneity of variances. That means spread is even. And the observations should be independent. So before we start looking at each one of them, I know you guys are thinking about within groups, like what does that mean? So let me explain that. ANOVA has 3 groups, right? Like more than 2 groups. In this case, it has 3 groups: placebo, low dose, and high dose. So what we are saying within groups means within one group. We're not talking about between the groups. We are talking about within one group. That means within placebo, within low dose, and within separately, within that groups, they are normally distributed. Okay, so that is what we want to look at. So let's state the criteria for assumptions. So for the first assumption, for normally distributed, we have 3 criteria. One is we will look at the visual analysis of histograms. Do they show normality or not? We will look at the p-value of the KS test if it is greater than equal to 0.05. And then we will look at the sample size if it is equal to or about equal, that means more than 30 degree, more than 30, I'm saying more than 30. For data to be an interval level, so dependent variable, for homogeneity of variances, we have the Levine's test is greater than equals to 0.05, and we will assume homogeneity. And then the observations are independent. So let us run some reports to see first the normality of the data set. So I'm going to bring back my data set. Here is my data set. So I go to Analyze, Explore. So the dose of Viagra is placebo, low dose, and high dose. So that is my factor list. The libido is my dependent variable. So I am going to click on this, and then this is, and I want to make sure when I click on the statistics, it is 95%. And I am going to say, okay, let me see what happened. Oh, it came. It just was taking a minute. So here you can see I have all the statistics run, and here is my confidence interval group. Oh, I did not click on histograms. So let's do this one more time. So I go to Analyze, Descript, Explore. I have to click on histogram. That is why it gave me a stem and leaf plot. And I'm going to just do normality plots with test so that I get the KS test also while I'm getting the histogram. So I'm going to press continue. So here is the histogram. So this is the histogram for placebo. This is the histogram for low dose. And this is the histogram for high dose. So you can see, like just looking at it, they do not satisfy the normality. I know that n is not greater than equal to 30 also. So let's look at my KS value. So here is my KS value. But if I look at my KS value, the significance is 0.2, 0.2, and 0.2. That means for each of these cases, each of them, it is greater than equal to, or rather greater than 0.05. So the normality is satisfied. So the condition, the assumption for normality is satisfied because 0.2, 0.2, 0.2 is greater than 0.05. Even though the visual were inconclusive, I do not know, and the n is not greater than 30, but because KS test says that they are satisfies the normality, it is. Okay. So now the next assumption is the interval. One assumption, if I look at that, yes, my dependent variable is in the interval. So that means it does satisfy this. It is verified that I have that. Okay, the next one is to look at Levene's test. So let us do the Levene's test. So to do the Levene's test, I go back to my Analyze. I go to Explore. When I am looking at plots, normality, I do untransformed and I say continue. Okay. And so my KS one was here. Here is my homogeneity of variances. So when I look at homogeneity of variances over here, based on the mean, because why am I looking at the mean? Because it is a scale value. Remember the data set, if it is an ordinal, I want to look at median. If it is nominal, I look at a different value of central tendency. So here, based on the mean, I see it is 0.913, which is again greater than 0.05. So my assumption for homogeneity of variances is also satisfied. So that one is satisfied. Now, the last one is to see whether the observations are independent. I assume that the data that is independent because one participant's score is not dependent on another participant's score. So it is again verified that it is independent of each other. So all the four assumptions that we have been satisfied. So here is the report, and here it gives you how to run if you want to run the Levene's test and things like that. And here is your table 1. That was the Levene's test. Remember how it was 0.913. Here is the KS test. It was 0.2, 0.2, and 0.2. The lower bound of true significance. And I have Liffey force significance correction. Here is your histograms that I have put over here. This one is the placebo. It says placebo here. So you have a PDF and a Word document uploaded. So if you cannot see it in a Word document, you can actually make the images go bigger also. So low dose, low dose. So here is the report. So if you see your document, you're going to see two things. Okay. Here what I did was I tried to put where the value is coming from so that you remember where it is coming. Like when you do yours and you have all these tables everywhere, you know where that value was picked up from. But when you report it, you are going to report without these superscripts and without any references. Okay, so this is the reason that I have it again typed here without any superscripts, without any references, so that you can copy paste this. So you will have a Word document that you can copy paste. So here is an analysis of the data showed that the assumptions for ANOVA were met. First, I assumed that the data was independent. So you can state it in any way you want. First, I assumed that the data was independent because they were sampled randomly. Levine's test indicated that there was equality of variances, or you can say there was homogeneity of variances, F2, 12. So where is this coming from? This is the table. This is the first degree of freedom. This is the second degree of freedom. We are looking at the mean because our dependent is a scale value, right? And this is my level of significance. So F2, 12 is equals to 0.09. 0.09. Remember, there needs to be a 0 before the decimal point and only 2 decimal digits. So if I go back, this third digit is actually less than 5. So I only report the first 2 digits and I put a 0 before that. P is equals to 0.913. That is what I get from the table. Although a visual analysis of the histogram was inconclusive, normality is assumed because of the results of the KS test with Lilliefom's significance correction and the p-value acting as the true significance, right? Indicated normality for the placebo group. D is the statistics. F is italicized. D is italicized. Where do I get this 5 from? Placebo, this is my degrees of freedom, 5. So D5, and this is the statistics. I only report 0.22. 0.22, and for low dose 0.22 and 0.14. Why? Because this third digit is actually more than a 5. And this is my p-value. So D5 is 0.22 with P equals to 0.22. And then the low dose D5 is again 0.22, P equals to 0.200. And then the high dose D5 is equal to 0.14, P is equal to 0. So this is all from table 3. Note that the p-values of the KS test are lower bound of the true significance. This is where it's coming from, lower bound of the true significance. Furthermore, ANOVA is known to be robust to normality. You just have to write that statement. You do not have to write the reference when group sizes are equal as they are here. So my group sizes are equal and it is robust to non-normality. So this is the way you write an assumption report for ANOVA. And so here is a clean copy that you are going to use when you do your assumptions. So now that all the assumptions have been met, and our report for the assumption is done, we are now actually going to run the one-way ANOVA. So as you're going to see, I actually have some of the images from the SPSS if you want to run it and see it. But let us first run the one-way ANOVA. I go back to my go back to my SPSS. I do analyze. I want to do compare means and I want to do one-way ANOVA. My dependent is my libido. My factors is the dose of Viagra. So I put that over there. I want to make sure that when I do the... So here is my post hoc, and like I said, I'm going to run a post hoc test with one-way ANOVA, and I'm going to make sure that it is 0.05 and press OK. I want to definitely check my options. I'm going to probably click on descriptive. I already have the homogeneity. I really don't need anything else, but why not? Let's just see what happens. Okay. So I'm going to do OK. And here is all these things that are there. So here is my main ANOVA table. So I'm going to go back to that so that you guys can see it. So if I go down, these are the plots, and here is that table. So for ANOVA table, for the libido, I have between groups. That means between any of the two groups, my P actually comes out to be 0.025, which is less than 0.05. That means there is a statistical difference between the three groups. Now, I don't know the differences between which groups, but I do know that there is a statistical difference. So my p-value is less than 0.05, which means I reject the null that there is no statistical difference. This is my f value. Remember, how will I report my f value? 5.12, because the third digit is more than 5. So now I remember how I had already clicked on the 2 key. So I am going to go and look at my 2 key results. I'm going to come back to these tables, but let's look at this. So this is my 2 key table. And if I look at it, this is your placebo with the low dose, placebo with the high dose. Low dose with the placebo, low dose with the high dose. So you see that it is checking each one with each other one. So placebo with the low dose, I have a 0.5. It is not less than, the significance is not less than 0.05. So it is not significant, placebo and low dose. But placebo and high dose, it is significant. So that is why you have a star there. It is significant, 0.02, which is less. Low dose and placebo is not. Between low dose and high dose, it is not significant. Again, it is not less than 0.05. But high dose and placebo, it is significant. So it's the same thing. Placebo and high dose over here, plus high dose and placebo. So whichever way you ran it, it is significant by 0.021. So it is less than 0.05. So now let us look at the other tables that is there, that you have. So we should have really started with this table that gives us the descriptive statistics. As you can see, placebo had 5, low dose had 5. This is the N in this. There's the median, the standard deviation, standard error, lower bound, upper bound, the minimum and the maximum for each of them. This is a plot to just show you the mean libido, and it is plotted to just see a visual of it. So this was the table that was there that says ANOVA with contrast. So this table is basically results of the Bronze-Fornett and the Welch test, which would be done if the homogeneity of variances had not been assumed. That means if the Levine's test would not have said that there was homogeneity of variances. Ours was, so we don't need that. But if we look at this one, we will see even when it's not assumed, it is significant. P-value is significant. So that is like reassuring from multiple statistics, whatever story we are trying to say. Okay, so this is what it looks like. Now that we know it is significant, we want to do a postdoc, and we had already clicked on the postdoc, 2 key postdoc, and so we want to see what that is showing, which we have already discussed about the significance here. So if we look at this, our F statistics is 0.05 between the placebo and the high dose. So we can say that there is a statistical difference between those two groups. Now, what if we want to look at the planned contrast? So let's look at the planned contrast. So the planned contrast, for planned contrast, we are going to compare means, one-way ANOVA. We have this. When we look at the options, I want to do these options which we've already done. And that table is actually already there. So this is the table. If you're looking at linear, the contrast, the planned contrast is, this is the line that gives you that is 0.008. So remember, you only do one of the other things. Either you do the post hoc test or the planned contrast. And in our case, we will only be doing the post hoc test, but it is planned contrast. So we can reject the null for the planned contrast to say that there is a statistical difference. And so there is linearity in the means that when it is going. So we reject the null that means are not linear. That shows that the means are linear. So one of the other things that you have to do in this is the effect size. The effect size for independent and dependent sample t-test was simple because I just did z divided by square root of n, which was there. But the effect size for ANOVA is a little bit different. And here is the website for it, and here is the formula. I am actually going to post a separate video on the effect size so that you guys understand this, because I don't want to make this video too long. But let us look. So this is what you get with that effect size, and you will have that video. So when I look at the effect size, this is omega square is the effect size. And then your HUC on page number 223, and then the fields book says the effect size of 0.01 is small, 0.06 is medium, and then 0.14 is large. So this 0.35 is very large. So it's a really good thing. How do I report it? Okay, so once again, you are not to put any subscripts, superscripts, or anything like that. This is, I'm doing it so that you know where the value is coming from. So for the omnibus test, there is a statistical significant difference of Viagra on levels of libido. So the dose of Viagra on levels of libido, F2, 12. I go back to my contrast table. This is 2 is between the groups. Within the group is 12. So this is where the 2 and the 12 is coming from. And this is my F value. This is my P value. So P is equals to 5.12, P is equals to 0.0. This is where it's coming from, table. And effect size is 0.35. Remember, I'm going to post a video on the effect size that is 0.35. 0.39, 0.35 calculations, that's okay. The mean, standard deviation, and 95 confidence are presented in table here. So I put a new table down here. So placebo with the, here you are going to put the A, and you will put an A because you are saying means sharing a common subscript are statistically significant as alpha is equals to 0.05 according to Tukey's procedure. So here is the ANOVA, here is the Tukey, and here is the planned contrast. So between, when you report the results, either you do AB or you do AC. So that's how you do this. So additionally, the results of Tukey's HSD postdoc test indicated that only significant, statistically significant mean difference was between the placebo group and the high dose. So I give the median. Sorry, this is the mean difference is 2.8 comma P is equals to this. The mean difference between the placebo group and the low dose was mean differences here. Where is all these values coming from? This is the table that these are values are coming from. Here is the mean difference. So between placebo and high dose, it is 2.8 with P value here. I'm only reporting the absolute values. Low dose and placebo is 1. Here is the P value. So all this is coming were not statistically significant. So the only one significant is the placebo group. So here is given the placebo group, the mean, the standard deviation, the 95% confidence intervals. All of these values are coming from here. This is the placebo group. What is the mean for this one? What is the confidence interval, lower bound, upper bound? Wait, this one, the mean placebo. Wait, these come from the descriptive statistics. Where is that table of mine? Here. So here is mean. Here is your standard deviation. Here is your lower bound, upper bound. Here is your mean, standard deviation, lower bound, upper bound. So make sure you guys don't get confused between the different tables. This is the table to give the mean difference, and to get the mean and the statistics is the descriptive table. Descriptive statistics right over here. So here is when I report the post hoc and the ANOVA. But when I do the planned contrast, then I say planned contrast. So in addition will come right after the ANOVA, okay? A planned contrast indicated that there was a statistical significant linear increase among the placebo group, low dose group, and the high dose. Remember, this was our research question. That's where it's coming from. And then I have F1, 12, which comes from this one here between the groups, because I'm looking at the linear contrast, and within the group is 12. So that its degrees of freedom is, and here, and then it gives you the value, one digit before the decimal, 2 digits, p-value. It comes from table 5, and once again your omega. So I put a clean copy over here. Once again, I want to make sure that you understand this very clearly, that you don't put any references or anything. And we are doing mostly the post hoc. So you're going to report on the ANOVA and the post hoc table till here. This is the planned contrast. So where this one, it's talking about, I gave you a subscript here so that you understand that it comes from between the groups, and the second comes from within the groups. So that also, it helps you understand that. This is the line that shows the post hoc differences. This is the line that shows the post hoc differences. If you have planned contrast, you won't report this. So basically, that's what we are talking about, is if you have a planned contrast, you're not going to report that part. But you are going to do the ANOVA and the post hoc. So that would be there. All right, best of luck. Once again, if there are any questions, please do let me know. I am happy to answer any of your queries. Have good luck.